you. It's probably one of the most boring days I will ever teach, and I apologize ahead of time. There's just nothing I can do to make this one more exciting. All right. Now, what is it? It's a dynamic condition in which two or okay. Let me preface this by saying, in case I say something really dumb, or I write something down really dumb, I have this thing called geographic tongue for any of you who know anything about that. They changed one of my medications yesterday. One of the side effects is it makes me really confused, apparently. Hopefully, I won't do anything really weird up here on the board. But if I do, I apologize now. So if I erase a lot today, it might be one of the side effects. The dynamic condition in which, yes. Geographic tongue. You know how your tongues are really pink and they look normal? My tongue doesn't look normal. I have all these white spots on my tongue, and the white spots move around. They don't stay in one place. So it looks sort of like a map all the time. And I know.
That's real?
Yeah. Just Google it so you can see all you want to know about geographic tongue. And so, and I have all these fissures in my tongue, which are these little cracks. And so about 2 years ago, it started. And so about, I don't know, a year and a half ago, they started treating me for it. And about 6 months ago in particular, I really got annoyed because it wasn't getting better. So they sent me to a mucosal dermatologist, which is a really high dollar specialist. And he even works at Cornell in New York. He travels from there, Wake Forest Baptist. Really nice guy. So they put me on a new medication yesterday. It's supposed to help the nerves in my tongue because when I eat, my tongue burns. With a lot of food, and it's really highly irritating. Only the nerve medication that they put me on is making me a little loopy. So if I write something on here that seems a little odd, please say something, because I might not recognize that it looks a little odd. Okay? I'm on nerve medication now. Yeah. Yeah, it's just bizarre. My kids think I'm just gross. Okay, so, I mean, it's not harmful. It's not an issue. The doctor says it's sort of like diabetes or asthma. It's just a condition that you treat and you get it under control. Only mine is not under control and it's inflamed. Most people have one little patch. My entire tongue is covered in it. So, you know, I'm really special. I have no idea. I've had it for years, but it's just really gotten out of control. Most people don't have it. Less than 3% of the population has it. And even a smaller percent of the population has the burning sensation. I am a very rare breed. Okay? So, even he said that this is very atypical. So, but the medicine is, I can feel, even I don't feel right today. Now, a dynamic condition in which, whoops, I left out a word. In which two opposing, I told you, I don't feel right. I might need to cut this stuff back. In which two opposing chemical or physical, I didn't feel right. No telling what I'm going to put up here today. A dynamic condition in which two opposing chemical or physical reactions occur at equal rate. Yeah, I think I'm good now. Yeah, I think I'm good. Yeah, I'm good. I'd give a close one. I'm good now. It also causes a few shifts in personality too. That's not a lot. No, okay. Maybe I'll start being nice for a period now. I doubt it. Go home at 30. Need color.
Oh, there you go. What is it? In the middle. Okay, okay. All right. Yeah, that one.
There we go.
All right, then put the wheel. Okay.
Not that confused.
Yeah, no, there we
Not
go.
that confused. All right. Now, what are the two most important parts of that definition? All right, I like one part of that. Which part do you think I like? Equal rate. All right. All right. Equal rate. All right. The two most important parts that we're going to focus on today are going to be the equal rates and the two opposing reactions. All right. So the two most important parts are we have to have two opposing reactions and we have to have equal rates. Now, yes, the reactions can be either chemical or physical. Now, today we are only going to talk physical reactions. However, we will do chemical reactions possibly Friday. I suspect more like Monday. Okay? So we will do chemical equilibrium, but I divide them up. Okay? So we're going to do chemical equilibrium with math. For those of you who like math, it's one of the easiest topics we do all year. So almost everybody likes chemical equilibrium because it's very, very easy. With the math, the part they don't like with chemical equilibrium is the shifting and figuring out which way equilibrium will shift left or right based on the rule. That's the part people hate. Okay? Chemical equilibrium is complex. I think physical equilibrium is pretty easy. Okay? But these are the two important parts. Everybody got it? We're giving everybody enough time to write. All right. So, what are we going to do with equilibrium today? Today, we're going to talk about a closed system to illustrate this. And we're going to use the system that the state wants you to understand, which is just a liquid vapor system. So, if we're talking about a liquid vapor system, we're basically talking about evaporation and condensation. Now, we could use this example with any of the phase changes we talked about yesterday. We could do this with melting and freezing, or we could do this with sublimation and deposition. However, because the state expressly talks about this example in this system, this is the one I'm going to explain because this is the one you're likely to see a question about on the exam. That's not to say you can't do it with every other system. Is everybody okay with that? Okay. So, essentially, we're going to do this with three boxes. You're going to get tired seeing these boxes. Okay. So, we're going to have some water down here. Because, again, the state assumes that y'all can only work with water. Just like yesterday with the Q, not going to work with any other liquid. So, inside this box, let's just assume that the temperature is somewhere around room temperature, let's say around 23 degrees Celsius. It's not terribly warm, but warmer than it is in this room. So, if we have water in here, what do you know the water particles are doing? They're moving, okay? All right, when they have enough kinetic energy to break the surface of the liquid, they evaporate. Are we at equilibrium? Why not? All right. Why can't rates be equal? How many processes are there? There's only one process. All right. There's only one process occurring. There has to be two. There has to be a reverse. The only process that's occurring right now is evaporation. Sort of like if I got an ice cube out of the freezer and set it on the desk out here. What's going to happen to the ice cube? It's going to melt. It's going to melt on my desk. Does it have any way of refreezing sitting on this desk? No. It can never achieve equilibrium sitting out here on this tabletop. Okay? So, at the moment, the only thing that water is doing inside of that container is what? Evaporating. That's it. That is one process. It cannot be at equilibrium when all it is doing is evaporating. It has to have a reverse process, number one. There were two requirements to be at equilibrium. It has to have two processes, and then it has to have equal rates. We don't even have a second process, much less have got equal rates. Okay? Are you with me on that part? Okay, so. Am I going back? I can. Then when I can go. Okay. All right, so if we have a same system, I put my evaporated particles back up here. All right, and I'm going to say evaporation continues. Right? My particles continue to evaporate up here. Now, what's going to happen if it continues to evaporate? Okay. So, what causes the condensation? All right, what happens up here that causes the condensation? All right, so the vapor molecule collide and stick because of attraction. Anybody remember what those attractions might be called? Because of polar forces, van der Waals forces, dip, all of those things y'all yelled out are correct. Okay? So, I'm going to write van der Waals. Dip, LDF. All of that stuff is correct. Okay? Those forces, all right, let me get my umbrella right here. Vapor molecules collide, they stick because of attraction, they become heavy, and condense into water droplets. Condensation begins. Van der Waals, dip, LDL. Dip would be polar, and LDF would be nonpolar. Okay, I just listed all of them. Because we're using water, it would be dip or hydrogen bonding. But if you had a nonpolar liquid, it would be LDF. Okay. Yes, they still work. They're just not as strong. Okay, it would be a weaker attraction, but they would still work. Okay. So, are we at equilibrium? Are they at equal ratio? No. The answer is no. We have two processes, rates are not equal. Now, this is the part where it's very important to understand. If they don't say to you in the scenario, the question, the whatever on the test, that the rates are equal or you are at equilibrium, can you make that assumption? No. Okay? So that's why up here I put evaporation continues, condensation begins. Did I say anywhere in this little scenario we were talking about that the rates of the two things were equal? No. Okay? When we get to the math sections and we're calculating, I will say we are at equilibrium or a system at equilibrium, so you know that you're at equilibrium. If it doesn't say that, can you just assume? The answer is no. Yes, that would be a Chem 2 or a Chem topic. You could then use the reaction quotient. All right, you have a shot. Okay. Yep. I told you were going to start them. Yep. What the world? We haven't got shifting yet. It's all right, so equilibrium is achieved when the rate of evaporation equals the rate of condensation. Now, here's where the misconception comes in. Did I say the amount of water equals the amount of vapor? No. I said the rate at which the water changes the vapor equals the rate at which the vapor changes the water. Okay? Now, it's sort of like going to Walmart. Okay? If 4 people go into Walmart and 4 people come out of Walmart at the same time, we have equilibrium. Okay? The rate at which people enter has to equal the rate at which people do what? Exit. The rates have to be the rate at which people go in have to equal the rate at which people come out. Now, did I say the number of people inside the store have to equal the number of people outside the store? That's irrelevant. The rate at which something happens has to equal the rate at which something else happens. So the rate at which that change happens has to equal the rate at which the other change happens. Okay? It's about rate, not about amount. So I could have a little video. So I could have a container that has virtually no water and a whole bunch of vapor, or I could have a container that has a whole bunch of water and virtually no virtually no vapor and still have equilibrium. Okay? The amounts are irrelevant. If the rates in which they change back and forth are equal, I can have equilibrium. The amounts don't make any difference. Okay? Does that make sense? Okay. All right, what's your question? It could be, as long as the rates at which they change equal the rates at which they condense, yes. Nope, won't even use that. Most likely. Nope. We're not going to talk numbers. Not right now. Yep. Okay.
Will it ever oh yeah.
Yes, and we'll talk about how to do that. The amount, but on month, Friday or Monday. All right, now. What factor affects the rate of evaporation? There's two. And what one factor affects the rate of condensation? Cannot give you the same answer for condensation. You give me for evaporation. All right, I like temperature. Not the second one. It's not a bad answer. Just not quite what we want. Nope. Those are the two most common answers I get. Nope. You're bringing up the rear of the third one. Anybody play tennis? There it is.
One time I don't think
All right, if you play tennis, if it rains, what do they do with the water? They squeegee out. They spread it out on the court. All right, everybody thinks the squeegee sucks up the water. Squeegee does not suck up the water. The squeegee spreads the water out, so it'll do what faster? It'll dry, it'll evaporate faster. That's the purpose of it. They're just the roller that they use on the tennis court. Okay, we need to get you out. Yeah. Yeah, exactly. Okay. Basically, you just either way, a lot of ways you just dry the counter at the house, you squeeze out water, and then you wipe the counter on the table or clean up the house. You can spread the water out so it'll dry and evaporate. Okay.
Oh my God.
Oh my God. All right. So, what one factor affects the rate of condensation? Okay. So, you can't say temperature again. So, we go back here. What makes these particles condense faster?
Oh, man, he was heavy.
What would make them condense faster? You already got heat up there. Can't use it again.
Yeah. That was probably
You probably won't know the correct name, but I would take an off answer. You got the right concept. On the ballpark.
Oink, oink.
Volume is enough.
What's the thing outside? No, I don't want that.
Storm, not the track. All right.
Yeah,
All right, if I write the answer on the board,
First letter, first letter.
tell me what it means. So tell me what that means. All right, the number of particles.
Oh, yeah.
So, if there are more gas particles or more vapor particles, there are more to attract and collect, you're going to get more condensation faster. It's sort of like, have you ever noticed that on a humid day, if you have a drink or a cold drink, which one has more condensation on the outside? On a humid day or on a really dry day? On a humid day, there's more water vapor in the air, so it's going to get more condensation and the can will sweat faster. Okay? Because there's more particles in the air. No, concentration is about anything. It's not just about condensation. Yes, yes. You can do the brain thing. We're going to learn about concentration after the break. Okay. All right. So now, looking at what we just talked about. Using that same example we just walked through with equilibrium, we're going to talk about Le Chatelier's principle now and when we do chemical equilibrium. Le Chatelier is not going anywhere. We're going to bring him back at the end of the week. If we don't get him Friday, he'll be a heavy presence on Monday. All right? But he'll be back early next week. Le Chatelier. He's not Le Chatler, even though next week y'all are all going to say, oh, that's not Le Chatler. He's pronounced Le Chatelier. He even has a little, like, house symbol over his A that I don't usually write up there. All right, let's see if I can get this right in my fuzzy brain. If a system is subjected to a stress, the system will automatically adjust to minimize the stress. Now, there are three stresses that we're going to work with. Not all today. One is temperature, two is pressure, three is concentration. The only one we're doing today is temperature. Pressure and concentration we will do when we do chemical equilibrium probably early next week. I suspect we will not get to chemical equilibrium until Monday. Okay, we're going to do temperature today. Like we're going to raise the temperature on system equilibrium, and we're going to talk about how it's going to adjust itself. was in equilibrium and we're gonna alter. He is pressure. No.
Ms. Wall,
Yeah. Yes,
do you have a Shia Donnelly?
I do.
Can you send her to the ninth grade principal's office, please?
I will.
All right, thank you.
You're welcome. Yeah, you've been hanging out with ninth grade all the time. Take the other one. Jordan took one to get her medicine from probably Miss Floyd. Just take the other pass. I got two of them on the back side of the door. Take the other one. I got two. I don't like wearing that. I feel bad. Yeah, I feel bad too. This part. Alright, so if everybody's caught up. Moving on. We gotta get through boiling today. If I don't make it through phase diagrams, it's fine. Alright, otherwise y'all can be stuck watching YouTube tonight. Because I'll get through that in fourth period. I did their whole lesson yesterday in 45 minutes. If I hadn't had to go to the doctor, I'd have probably caught up on Fridays too. Alright, so taking the same boxes that we started with. Okay? Same box. Okay? We're going to increase the temperature. Going to increase by temperature. Everybody okay with my symbols there? Increase T? Now, what's going to happen inside the box if I increase the temperature? Evaporation. Okay? Oops, I forgot to throw my gas in. Okay? What's going to happen? Evaporation. We don't have to worry about the pressure. Now, Daniela has jumped way ahead. All right, back up a little bit. Past. Okay. All right, so the water molecule. All right, so the water molecules move faster. They have more kinetic energy. Okay, they break the surface. Faster. Evaporation increases. So, equilibrium is disturbed. Okay? And I should probably write it here at the top. We were at equilibrium initially. We were taking that same set of boxes I said, but I didn't actually write that down. So y'all won't remember that when y'all are studying these notes. That I said that. So you better write it down. And Emily and I were just Emma. Yeah. Emma and I were just talking. That might help my tongue to kill my brain. All right, we were just talking stuff from Friday, stuff from yesterday, and the very, very early part of equilibrium, not this deep into equilibrium, like the definition and maybe the first three boxes. The conditions that alter equilibrium, Le Chatelier, none of that would be on the quiz. Okay, just the very beginning, like the definition and maybe the first three boxes, that would be it for the quiz. Come on. Yeah, the very beginning of equilibrium only. I did you pay. No. I told you, the police stop very early on in everything, starting with the notes you took, starting to solve it, you have to go Friday. As long as nothing changes out of here on Thursday afternoon. I'll be in the office until about 4:15. I should be. As long as nothing changes, I will be here the rest of the week. Yes, ma'am. Huh? The last word is disturbed. As long as nothing changes, I don't have to make an emergency trip home. I'm probably gonna wind up being after Christmas. Unless I decide to split it, which I sincerely doubt I do, it will be after Christmas. Okay? Now, so if the equilibrium has been disturbed, the question is, how does it go and get back to equilibrium? Okay? So, the evaporation's been increasing, right? So, if the evaporation is increasing, that means what's happening now? Okay? You now have more what forming up here? What's happening up here? All right? You now have more vapor forming. Okay? You now have more vapor forming. All right? If more vapor is forming, then you're going to wind up doing what? Okay. Your rate of condensation will increase. So, eventually, equilibrium will be re-established at a faster rate. Now, question. Ask yours before I ask mine. That wasn't what I was going to ask you. You're asking me that? Because you had, I increased the temperature, right? So what happened to your rate of evaporation? That's right. Your evaporation increased. You said your rate of condensation increased. So that's why your rate increased. So if I, let's say, lowered the temperature, if I reversed it, let's say I lowered the temperature, what's going to happen to our water molecules? They're going to slow down. So if they slow down, what's going to happen to my rate of evaporation? It will who? It will lessen. Okay, that's a good answer since I wasn't sure what you said. All right, so my evaporation is going to slow down or lessen. So what's going to happen to my amount of water particles that turn into vapor up here? It'll who? It'll decrease. I have less vapor. So what's going to happen to my condensation? It'll decrease also. So I have less vapor. I have less condensation. So what's going to happen to my rates? It'll be less. Okay, so the question I was going to ask is, what happens to my amounts of water and vapor? So when I increase my temperature, what happens to my amount of water? Okay, so my amount of water decreases. What happens to my amount of vapor? It increases. In this case, yes. Because if you increase the temperature, it turned into vapor and the water goes away. just like sort of like when you go home and heat water to make rice or noodles, right? If you leave it sitting on the stove for too long, what happens to the water? It's gone. Well, yes, it does. It vaporizes, right? We don't say it evaporates, it vaporizes. Y'all are more intellectually sound now. Sure, you will be here in a few minutes. Everybody with me? Everybody got it? Because we need this to talk about boiling. All right, let's start boiling. All right, yesterday I told you boiling was different. Well, hold on. Let's talk vaporization.
What's on the floor?
Just put that above it.
I'm so sorry.
All right, so yesterday, and I can't remember what I did yesterday, which is why I did this. All right, I told you yesterday evaporation and boiling were types of vaporization. First of all, evaporation applies to a non-boiling liquid. Okay? And boiling, we're going to talk about in a minute. So how can you tell something is evaporating versus something that is boiling? Okay? That is one clue. Okay? Something that is evaporating, first of all, has no bubbles. It also happens at a large range of temperatures. Whereas boiling is going to happen at a specific temperature. Okay? We know that we're going to see bubbles when we boil. It's going to happen at a specific temperature. One thing that a lot of people don't realize about boiling is boiling happens from the bottom, whereas evaporation happens from the top. Because evaporation generally happens from a heat source such as the sun, or perhaps the heat in your room when you dry the table. It may come from the light over the dining room table. Okay? Those are three differences about evaporation and boiling. There are others that we can talk about, but those are the three main. Now, how does boiling work? Work different from probably breakfast. No. I'm a mess today. All right. How is boiling? Yeah. All right. Does everybody have that part? So we can talk about the definition. Okay. Now, everybody just assumes that boiling is to change from a liquid to a gas, which it is not. Get my wording right here before I write it down. Everybody yells at me. It's not. All right. All right, the temperature at which the equilibrium vapor pressure equals the atmospheric pressure. So we were talking about. Yes. I had something. Now, most people can tell me that the boiling point of what is what? 212 Fahrenheit or 0. That's what I thought. Yeah, it's on the freezing point. All right, now, These are averages. If we were to boil water right now, we may or may not get that number. Because what in that definition causes that number to be different? Atmospheric pressure, okay? When you took our science and talked about weather, somebody should have talked to you about high pressure and low pressure. I hope. Okay? Like on a sunny day, we should remember that that's what kind of pressure? High. And on a rainy day, it's what? Low. So if nothing else in your weather unit, you should have got those two things. Okay? Alright. Don't have to work on my bad art drawing here, but you got to get that. No. You're drawing the stove with a pot. Yes. Alright. You gotta work with me here because that's the best I can do. I just had Miss Thompson to come draw my picture. Now, I'll just stretch all that. Now, moving on. So we got a pot on the stove. When you have this pot sitting on the stove, when does it boil? Same concept is equilibrium. Okay? Now, this burner heats the water. Okay? So think about this. Heat is transferred to the water. The molecules move faster. When enough kinetic energy, they break the surface, right? So, when these molecules break the surface over here, they run into cold air. Now, what happens when they hit that cold air? Those hot molecules hit cold air, and they do what? They condense. They go back down. Okay? Now, more molecules evaporate and condense. This creates equilibrium, vapor pressure, above the pot. Okay? So right here above this pot is equilibrium, vapor pressure. Okay? More molecules evaporate and condense. You create equilibrium vapor pressure above the pot. The pressure continues to increase as the pot heats. Okay, that pressure continues to increase as the pot heats. The P, the pressure. So this pressure above that pot continues to increase. It evaporates and condenses. It evaporates and condenses. It evaporates and condenses. There's still cool air above the pot. If you feel, I don't recommend you do this on your stove, but if you actually feel around the pot on the stove, how's it going to feel? Yes, but how else is it going to feel? Wet. Why is it going to feel wet? If you stick your hand over the pot, how's it going to feel? Wet, because what's the pot doing? It's evaporating. All right, if you put your hand over it, you're going to feel all that moisture coming up, and that's the vapor condensing on your hand. Well, it's going to condense on your hand. All right, but that is condensation coming back down into the pot. Okay, now that continues until what happens? No, you do not see boiling until, okay, you do not see boiling until the equilibrium vapor pressure above the pot equals atmospheric pressure. Okay? I abbreviated some of that. Okay? You do not see boiling until the equilibrium vapor pressure above the pot equals atmospheric pressure. So, on a high pressure day, it's going to have a higher boiling point because it's a higher pressure. On a low pressure day, when it's rainy out, the boiling point is going to be a lower day. It's going to be a lower boiling point.
Oh, so was that whole thing where it's like they're running much world and they got malnutrition and stuff. Oh no.
Yes. Very helpful. Okay. So, is everybody caught up with me? Everyone, you got it. We're going to draw North Carolina and do the same thing. You think you can't draw? Wait till you see this. You go low. Everybody caught up?
Like that hand on my pot, like, I know. I think I tried to draw it. I'm not in a heart rate monitor. Right.
Alright. You got some hills, you got the mountains, you got some coasts. You've been to all three areas, it's not far off. Now, where's the greatest pressure in the state of North Carolina? Okay.
No, it's my closest. It's mountain, not like one person. Oh, yeah.
Oh,
Right? No, I thought it was like that. No, I get to Appalachian too much to where my ears pop to the pressure.
Alright.
Yeah.
Coasts have greater pressure, mountains have lower pressure.
Don't
Got lower pressure. So,
Oh, that's why you're in the ocean. It's higher.
if
Oh.
If you have greater pressure down here at the coast, based on what we just wrote down, if I cruise back, okay, you don't boil until you reach what? Atmospheric pressure. If you have greater pressure down here, you're going to have what? A higher boiling point or a lower boiling point? Higher. You have a high, oops, change colors here. You have a higher boiling point here, and you have a lower boiling point here. So, any of you who bake, if you bake at higher elevation, it tells you on the side of the box that you need to cook it for what? That much longer. Because at higher elevation, it takes longer to cook it. It cooks lower because it cooks at a lower temperature. At the coast, it cooks faster because it cooks at a higher temperature. Because you have greater pressure at the coast, it's going to cook faster. It reaches its boiling point faster because you're at a higher atmospheric pressure. We're sort of in the middle of Piedmont. Huh? No, it wouldn't matter inside. It's all about elevation.
Oh, you mean like outside?
Yeah, it's about the elevation.
That's why
I have no idea. Yeah. Most of it's about elevation. Alexa. Yeah, because you have a greater elevation, you're gonna have lower pressure. Now, I only have something very simple for you to do for homework tonight. It's with equilibrium. It's very short. Your homework is to study for your quiz.
It's like fire. You like next to the fire on the mountain. It's fire.
Or if I know, no.
I was the same
Did everybody get one? If you need to do makeup work, I'll be here today. Remember the deadline I set. I'll be here today, tomorrow, and Thursday, and next Monday is the last.